We have a chapter which name is units and dimension. In details, we will understand. We will see it in details. Whatever will be possibility from our side. So, as you know, this is the first chapter. It's a first chapter of class 11, and yes, most of you would be watching this as a revision as a beginner. Okay, I don't know, but here I am here to explain it in details. We will start from basic and then we will enter till the advanced. So let's start with discussion of units. Okay. So here first we have physical quantity. Look, in the world you will see that there are there are a lot of quantities. Yeah. So we can classify all those quantities into two parts. First, physical quantity, and second, unphysical quantity. These are two parts that can be classified, all those quantities that are present in our world. Okay. So unphysical quantity we will ignore it, and physical quantity we will discuss it as a chapter in this section, in this lecture. So here, let's see what are those unphysical quantities, what are those physical quantities. So look, it's physical and unphysical. It's all about measurement. Whatever quantities, let's say you took a quantity and you are not able to measure that quantity. So if quantity cannot be measured, then those quantities are nothing but non-physical quantity, because we are not able to measure anyhow. Okay, clear? So I can give you examples. For example, love, hate, or fighting. Okay, fighting a speed, not intensity of a speed, not a speed, sound, I would say, sound, light. Okay, so intensity of light is a physical quantity, but only light is not considered as a physical quantity. Okay, I hope you are understanding very well. Now try to understand further. So you have understood what is a unphysical quantity. So physical quantities are those quantities which cannot be measured. Crying, laughing, these are quantities that cannot be measured. Okay, whereas we have physical quantities. I will give you examples. Okay, so physical quantities are those quantities which can be measured, which can be measured, hmm? which can be measured. For instance, this marker, so height of length of this marker will be something, would be something. So we are able to measure. We will be able to measure this marker. So that's why we can say this is a quantity. But name of this quantity is what? Physical quantity. Which type of a quantity? Physical quantity. Okay, because it can be measured. That's all. So I hope till here you have understood about physical quantity and unphysical quantity. Now you have understood meaning of unphysical quantity. Here you will ignore discussion of unphysical quantity. Our focus will be on physical quantities, not unphysical quantities. Clear? So let's move ahead. So physical quantity. Now next word is nothing but measurement. How do you measure anything, any physical quantity? Tell me. Most of you, some of you would be measuring by taking some tools, of course, a scale, a ruler, a compass. Okay. Mm, Even more thing, there are more tools that can help us to measure some quantities. Yeah. So of course we measure. If I say how will you measure this marker, then of course you will bring a scale and then you will put over this marker. Then you will see, yes, this much. length of this marker is this much. So you were able to say that yes, length of this marker is this much. How? Because you used measurement tools. That's why. That is how you are able to measure. Okay. So when you will pronounce your measurement. So how will you pronounce? For example, you said that 5 centimeter. Length of this marker is 5 centimeter. Okay. So that is how you will say to someone. That is how you will say to someone that height of this marker is 5 centimeter. Mass of rice is 2 kg. So 2 kg. Now let's break down this 2 kg, this units. Okay. So 5 is a number we can see. But this is cm is what? Chief Minister, no, centimeter. Okay, centimeter. Can, can't we say 5 only rather than saying centimeter? No, it will be wrong. It would be wrong. You will not get clarity. People will not get clarity by saying only 5. This can be anything. But when we add this is centimeter, then people are able to interact with this number. People would say yes, 5 centimeter is a length of something. Yes, that is how we and people are able to interact with any number, with units. So remember, this 5 is a number, this is centimeter, that comes with number is nothing but a unit. So it is known as a unit. Okay, unit. I hope you got it. Unit. So this n, which is number, and this is a u, unit. Now here, with example, let's understand. We have an example, which is mass of a stool, mass of you can say table. Okay, mass of a chair. So mass of a stool is a 15 kg. Mass of a stool is a 15 kg. So here you can see 15 is a number, kg is a unit, and this property is known as a Q. Q stands for physical quantity. So measure of this physical quantity is how much? 15 kg. That is what we are saying. So from this you are understanding that Q will be is equal to nothing but NU, where N is a number and U is a unit. Clear? And Q is a physical quantity. I hope you understood something. You understood something. Just have a look. Now, after this discussion, we should discuss about fundamental units, derived units. Okay, fundamental units and derived units. What is a fundamental unit? What is a derived unit? When we have fundamental quantities and derived quantities. Let's see this fundamental units. So remember we have a limited fundamental quantity. So I am going to write over here fundamental units. Okay, fundamental units. Seven fundamental units. Seven fundamental. These are seven physical quantities. These are seven physical quantities that are fixed fundamental quantities. Okay. So units of this will be unit for length will be I think m m and mass is measured as a kg. Mass is measured as a kg. Time is measured as a second. Okay. Temperature is measured as a Kelvin. Electric current is measured as a ampere. Luminous intensity. It is said that luminous intensity is not studied too much in 11th class or in 12th class. But okay, quantity of matter, mole, I think mole, molecules, mole. Luminous intensity, candela, city, candela, candela, city. These are symbols. These are also units. So meter, kilogram, second, and all these are SI unit. Okay, all these are SI unit. Kelvin, Kelvin, ampere, candela, candela. Molecules, mole, not molecules, mole. Only you will have to keep remember in your mind that are this five thing. I think so. This five thing: length, mass, time, temperature, electrical current. Okay. If you are starting, if you are beginner, so only this five. If you remember this five fundamental quantities or units, it will help you more in upcoming discussion. Okay. So remember, these are seven fundamental quantities. By the help of these seven fundamental quantities, we derive a lot of units, a lot of a lot of derived quantities. Okay, by the help of this seven fundamental quantities. But here I said that these are seven fixed. These are fixed. But when it comes to derived quantities, derived units, then it will be more. It will be more because here we will be driving by the help of a fundamental quantity. That's why number of derived units will be more. Okay, will be more. So this temperature Kelvin, electric current ampere, luminous intensity study, quantity of matter mole. If you ignore this luminous intensity, quantity of matter, it will run. It's okay. Now let's just say derived quantities. Okay, derived quantities. Derived units. Derived units. First of all, you will have to take a quantities so that you can take understanding. Derived quantities, I am saying. For example, we have a speed. A speed is a quantity, but which type of a quantity? Is it a scalar or is it a vector? We will see it later. Right now we know that this is a physical quantity, that's it. So what will be unit of this physical quantity? This is a cube. So I think unit should be what? Meter, kilometer, meter or kilometer. Okay, meter per second. Yes, okay. Meter per second. Here we have two units. Two units. First is M and second is S. So this is not this speed is not independent. It's dependent on the fundamental units because it is driving by the help of two units. That's why we are saying this is a independent. This is a dependent on a fundamental quantity. You can define this fundamental units as you can say that these fundamental quantities are independent and derived units are dependent on fundamental quantities. So this is a speed, and here we can see one unit is n, which is a meter, and second is a second. Second is a second. So there are two units. Okay, not only one. Now area L into B, which means M square. So here this is a two times, and then we have a square, which is a yes same. Okay, this was just example. We will see this derived units when we will be in the discussion of dimension. There we will see more derived units. Right now, as of now, just understand what are derived units, how to derive. We will see. Okay. Now let's just say dimensions. Dimensions. Now let's just say dimensions. Here. What is a dimension? In your language, how would you like to explain this a dimension word? Let me explain. Dimension is nothing but this is a power. Okay, this is a power. It will tell you that this same unit is coming how much times. So who will tell you? This a dimension will tell you. So here power will be times of units. For example, this a multiplier. So this 2 is nothing but dimension. So completely we can say they will represent a dimension as a MLT, and this will be surrounded by a square bracket. Okay, a square bracket. So here a square will become here. If m meter is 2 times, then here you will write 2. If l m is a mass, okay, not meter. If a kg is coming 2 times, so you can write as a 2 here. L is a 1, t is a 0. Here you are saying that kg a square and meter, then time is nothing. So kg square meter. That is what you are saying. That is what you are saying. So this complete is our dimension, where we represent frequency of units. Frequency of units is represented by the help of a dimension. Okay. Now here area is a quantity. You are already familiar that area is nothing but this is a quantity. Now here L, which is a length, and B is also length. This is a breadth and L is a length. So here we are measuring, which is in meter. Okay. So M, this is length, it is also length. So length is coming how much times? 2 times. So dimension of area would be nothing but dimension of area would be what? M. M is 0. There is no mass for area. So we will write it over here as a superscript. So superscript of M will be 0. Now L is a 2 times. M is a 2 times. That is what we are saying. Okay. So next T. There is no time. There is no time for area. So here superscript will be 0. Superscript of a T will be 0. Now you can say confidently that this is a dimension. M0, L2, T0. It's a complete dimension for area. There is no error in this case. Clear? Okay, we are clear. We are clear. Now here you can take more examples apart from this to understand dimension. For density would be nothing but this is a kg per meter cube. This is a unit of a density. But how to write a dimension of any quantities we have seen. Okay, we have seen. Now what should be dimension for density? Where we now unit of it. So unit is a kg per meter cube. So kg is nothing but a mass. Okay, kg is a mass which is 1 times. Okay, it can be hidden. If you want to show this, then you can write over here 1. If you remove this, so still this will be nothing but m raised to power 1. So next we have L. So L is a length. So length is coming how much times? 3 much times. So T is a 0. This is a dimension of this is a dimension for density. We can't say that this is a dimension for area. No, this will be wrong. This dimension is for area. This dimension is for density. What are you understanding by this dimension? By this dimension, you are understanding that M, which is a kg unit, kg fundamental unit is coming 1 time. and this length is coming 3 times until there is a no t present. That is what you are understanding by the help of a dimension. Okay, density is complete. One thing I would say here you can see this is it can be written as what kg per meter cube. So this per will be known as this per is nothing but it gives you a subtraction sign in a square. Okay, here we will have minus because per denotes to subtraction. Clear? Now next we have a speed. Next we have a speed. So distance upon time. Distance upon time. For distance, we know distance is measured in meter or kilometer. Okay. Meter upon time. You can also write it as a meter per second raised to power minus 1. Okay. So dimension for a speed will be m is 0, l is 1 time, and t is also 1 time, but it is in denominator. This was a dimension for a speed. It tells us that a speed depends upon l. It does not depends upon m. Dimension equation. Like that, we will take more physical quantity, and then we will see what are units of those given physical quantity. Then we will try to find the dimensions of all those physical quantities. Okay, so here as of now we saw only this one, two, three dimensions we saw. Apart from this dimension, let's see how much numbers of a dimension do we have. Okay, do we have? Next we have which is force dimension. For this second we have work. Momentum, then pressure or stress, moment of a force, impulse, I have I have I have written some more physical quantities so that we can get more clarity about the dimension. So let's start with force. You know unit of force is nothing. SI unit of a force is Newton. Okay. So Newton is also it can be written as what acceleration multiple distance mass okay mass m a mass multiple acceleration which is nothing but m. Okay. Now tell me, mass is one time, acceleration. So can you say m1? Okay. Now here acceleration is a meter per second square. Meter per second square. This is a SI unit. This is a unit for acceleration. So mass is one time and here n is also one time. But t is coming two times. m1 l1 t minus 1. m1 l1 t minus 2. Okay. That is how dimension is written for given quantities. First of all, you will have to find what would be unit of this given physical quantity. Then you will be able to find what dimension. Then you can find dimension. So next we have work. So you know that work is equal to force multiple displacement, not a distance. If there is a displacement after applying a force, okay, somebody applied force on an object, and that object that object did displacement. In that case, we can say work happened in the language of physics. Okay, so displacement should happen. There would be there should be displacement of object after applying force. In that case, we would say this is work. This work happened. Now here you can see we have force then distance. For distance f. So can't you say that f will be as it, and here m increased. So here was only one time. So this will become 2. T will be as it minus 2. This is our dimension of work. m1 m2 t minus 2. Now next we have which is power. So power is represented work upon time. Work upon time. Power. Work upon time. This is also easy. If you know what is dimension of a work, then you can also calculate a dimension of a power. So just here this power added a time. This power added a time. So work is nothing but m1 l2 t minus 2. So t minus 2, and here t is more, and this is in denominator. So of course we will replace t minus 2 by t minus 3. Okay. So m1 l2, and here this will become minus 3. Okay, because t is this t is in denominator. That's why. Clear? Now next we have energy. E-N-E-R-G-Y. Energy. Remember, it can be thermal energy. Okay. There are more energy. Okay. So for those units will be same. I think if units are same, so dimension will be same. You will observe. So here I am saying that if there are coming more energy with added other words, so units will be same. You know that unit for energy is joule. 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 So work and energy both are same. M1, M2 and T minus 2. Work and energy both are same. You will have to keep remember this energy M1 L2 T minus 2. Momentum, we have momentum. Momentum is equal to P multiple V. P multiple V. V is a velocity, meter per second. P is a velocity. P is equal to mv, I think. P is equal to mv. So mass, we have a mass which is nothing but one time L is also one time, L is a one time meter per second. So S is a denominator, this will be minus 1 because S is a denominator, that's why. So M1 L1 T minus 1. This is the dimension of a momentum where P is equal to M multiple V. M is a mass, V is a velocity. V is a velocity. Next we have pressure and distance. Moment of a distance is what Newton multiple distance. So next we have pressure. Pressure and distance. So force upon area. Yeah, there is a chapter of pressure. So it's nothing but force upon area. Force upon area. Remember, pressure or stress is equal to force upon area. If we apply, if area is less and if we apply more force, so momentum will be more. Okay. So area is less and force is more. Impact will be more. But area is more and force is less, impact will be less. We will see in details about this in separate lecture, in lecture of pressure. Right now, just understand, yes, this is equal to pressure. Pressure is equal to force upon area. Okay. Force will be applied on, there is an object, and on that object force is being applied downward. Okay, downward. So if area is less and force is more, so pressure will be more. Of course, pressure would be more. If area is more and force is same, in that case, pressure would be normal. Okay. Now let's see. We know that this is nothing but Newton, and force is a Newton. No. Uh, this kg and then meter per square. Kg meter per square. So here meter is coming again, which is area, and this is 2 times. Area is equal to m multiple m. So meter is becoming 3 times. Can we say m is 1 time? Okay. Then L is coming 3 times, minus 3. 2 is in this kg meter, no, hold on, kg m mass, kg for mass and acceleration, so meter per second square. So m1 and minus 2, so I think it will become minus 1. It will become minus 1. m2 and m1, so of course minus 1. Now t we have how much? 2 times, minus 2. So finally we got this dimension for pressure or stress. So M1, L minus 1, T minus 2. This is a complete dimension for pressure and for pressure or stress. So modulus moment of M1, L minus 1, T minus 2. Yes, this is correct. Now next quantity is impulse. Impulse is equal to remember impulse is equal to force multiple time. Impulse is equal to force multiple time. Force is a Newton. M1 L1 T minus 2. M1 L1 T minus 2 and time. So M1 will be as it, L1 will be as it, but T this will decrease. So T minus 1 because it is in multiplication. This is not in division. Multiplication, which means it is in numerator, not in denominator. So that's why it will decrease. It will decrease. I would say it will increase. It will increase. Minus 1. Okay. This was a dimension of impulse. Next we have volume. Volume is nothing but m cube. M cube. You can say m cube. M cube. Meter is coming 3 times. Length is coming 3 times. So you would say m is a 0, l is a 3 times, and t is a 0. This is a dimension for volume. Next we have the frequency. This it is said that frequency is equal to 1 upon time. 1 upon time. 1 upon time period. Okay, so frequency is equal to 1 upon time period. 1 upon time period. Okay, so here we would say m is a 0, l is also 0, but t is a minus 1. T is a minus 1. That is how you will write any dimension of any unit. You can say L multiple B multiple H. This M cube can be written as L multiple B multiple H. I hope you understood something from this part. Now next chapter, let's see. I want to stop this till here. We are going to start next chapter, which will be vector. we have vector. Now let's say this. Tell me, do you know about this? About this? Let's start this new chapter with scalar quantities. We saw, I have told you that there are two quantities that are present in our world, and that two quantities that quantities can be classified into two parts. We we divided those parts into two sections. So first physical quantity and second unphysical quantity. So we are our focus is on physical quantity. We have ignored on physical quantities. Okay, so any quantities, scalar quantities are those quantities. We are taking those quantities which do not provide a direction, they only provide magnitude. Okay, so you can say magnitude, but no direction, you can say this line, a quantity which does not have a direction but it has a magnitude. This type of a quantity is considered as a scalar quantity. That's it about a scalar quantity. Clear? Now next let's us see what is, with example I will give you more clarity about scalar quantity and vector quantity, don't worry. So let's just see vector quantity. Okay, so these are also quantities, but these quantities provide what? Direction with magnitude. Okay, so remember, those quantities which are providing direction with magnitude, so those quantities will be considered as a vector quantity. Clear? Now what's the difference between a scalar quantity and vector quantity? There is a one word which is coming to say that yes, this word is saying that yes, both are not same. A scalar and vector both are not same. Who would say this? A direction word is the same. Okay, in the case of a scalar, this is not providing direction, but in the case of a vector, it is providing direction. And you know, having direction is more important. Sometimes in some cases we can execute our values without a direction. Okay, we can convenience to other person without a direction. But according to requirement, if we do not provide a direction with a magnitude, then of course other person will not convince. We will not be able to convince to someone, okay, without a direction. Representation of a vector. Remember this vector symbol. This is a symbol of a vector. Okay, clear? Examples. So a scalar distance is an example of a scalar quantity. Velocity, displacement is an example. Displacement is an example of vector quantities. Because what's the difference between them? Difference is that distance is not providing direction, but the displacement provides a direction. That's why we are saying distance is a scalar and displacement is a vector. This was examples. Okay. So remember this arrow is nothing but vector. This is how it is represented. Any quantities which is a vector is represented by applying this symbol. Clear? Now let's see more thing about this symbol. This end side is known as a tail, and this head. This is a tail, and this arrow is a head. Okay, this is a tail, and this is a head. Are you understanding? Are you understanding? This is a tail and this is a head. This was more about vector. How to represent a vector? That is, for example, we have a vector which name is a. So this is not completely vector. To represent this as a vector, we will have to apply this symbol above this letter. Now it's a complete vector. We are saying yes, we have this vector. That is how we pronounce. Okay. Till here this part is clear. Now next is a type of vectors. So first we have negative vector. Okay? Negative vector. These are types of vector: equal vector, unit vector, collinear vector, zero vector is also known as a null vector. So here let's see negative vector. Remember, any vector, for example, we have this vector. A vector, a quantity which has a magnitude and a direction. So direction of this vector is in this. So negative vector is nothing but another vector should be in opposite side. This is another vector. So this should be in opposite side. But remember, magnitude of this and this should be same. For example, this is a 5 centimeter. So this should be also 5 centimeter. Then this would be definition for negative vector. Magnitude, in the case of a negative vector, magnitude of a vector should be same. But direction should be opposite. Let's say name of this is nothing but this, A vector. And name of this is nothing but B vector. We can also write like that. A is equal to minus B vector. So it is telling you that this is in opposite. Clear? Minus 5. It is enough about negative. Now next we have equal vector, which means there are two vectors. Okay, there are two vectors. Magnitude is the same and direction should be same. Is about equal vectors. There are two vectors whose magnitudes are same and directions are same. Clear? Now next we have unit vector. Unit, which means 1. So it is used to specify direction. Unit, you will observe that unit is being used to specify direction. Unit vector. So unit vector. Cap, do you know about cap? About cap. For example, a cap. So a vector which has a magnitude only 1. So this vector has a magnitude only 1. And work of unit vector is to tell the direction. So unit vector is represented like that. This is equal to vector A upon magnitude of vector A. Okay, magnitude of mod of vector A. So this A cap is equal to vector A upon mod of vector A. Remember, this vector A is equal to this A, this vector mod of vector A is equal to A. Here we removed direction by applying this modulus. So work of modulus is to remove direction. It is giving only magnitude, not a direction. So that's why we are saying this is equal to A. So here A is only magnitude. You can see there is no arrow above of this text of this letter. That's why we are saying this is a scalar. So this is equal to this. Here we applied mod, that's why. You never say that this vector A is equal to A. No, this will be wrong. This will be wrong. If you wanted to say that this is equal to this, then you will have to apply this modulus. Okay, this modulus. I hope you understood something. Now next we have collinear vectors. Collinear vectors. Look, they are here linear. Linear means in one direction, in one line you can say. It can be horizontally, it can be direction can be vertically. This can be between, a line can be between horizontal and vertical. Okay, but there would be line. There would be line. So here we are saying that there is a line, and on this line there are coming how much? There are more vectors. So remember, numbers of vectors, if they are in same line and it's not parallel, okay, it's not parallel, they are in same line, so these vectors will be collinear vectors. It is saying that numbers of vectors are in same line, they are present in same line, along a line, you can say along a line. Okay, now zero vector. Zero vector is noun. We can say zero vector is what null vector. So either you call it as a zero vector or a null vector. Both are same. So zero vector, which means magnitude is a zero. There is no direction. That's it. Magnitude is a zero and there is no direction. But it will come sometimes. Sometimes a zero vector will come. Right now, just understand magnitude is zero. From this word we are saying that magnitude is zero, direction is nothing. Direction is nothing. Now next, some laws, let's see. For example, first we have triangle law. Now next, triangle law of factor addition. Triangle law of factor addition. here. Right now we will see only one law, which is a triangle law of vector addition. There are more law of vector addition. Apart from this triangle law, we have a parallelogram, then polygon law. Okay, polygon. Uh, we use this triangle law when we have two vectors. Then a resultant vector will come. So of course we will at the end we will have three vectors. So that's why we use, because we cannot have four vectors, we cannot have more than three vectors. That's why if you have two vectors in your equation, then you can use this triangle law. If you have three if you have four vectors, then you can use parallelogram. Only parallelogram. If you have more vectors than four, okay, in that case you will be able to use polygon law of vector addition. Right now question is the same, that you have this one vector and another is this another is this vector. We are visualizing over here, we are visualizing, okay. So this is a one vector which is a and this is another which is a B, and question is saying what should be resultant, where you use what triangle of a vector addition. So here remember, we will have to shift without changing its direction. In that case this will go over here, so it will become like that, okay. So this resultant should be drawn oppositely, like that, okay, like that, clear. So this is a third vector which is known as resulting vector. Which is known as a resulting vector, clear. Now here we can say this AB, this will be equal to R, resulting vector. This will be equal to A vector plus B vector will be equal to R. So here we want mode magnitude of this resulting vector. In that case what will happen? This magnitude of R vector will be equal to A plus B then plus AB cos theta, like that. Yes, from this formula we will get the magnitude of the resulting vector. From this we will get magnitude of a resulting vector, but remember this is a square. So magnitude of a resulting vector will be equal to under root of vector A square plus vector B square then plus 2AB and then cos theta. Okay, this is just a formula to calculate a resulting magnitude of a resulting vector in the case of a triangle. Clear? In this case this is A and this is B and this is nothing but it's our resulting vector. Clear? This is also vector, but this is a resulting vector. Clear?